Okay, hello everyone. So I've made some updates to the notes. I've had a few comments, a couple of typos in section 2. I've redone all the sections, so just re-download the typed up notes. Put a couple of extra bits here and there. Okay, so the changes aren't massive, but they're probably worth referring to the latest versions. Okay. So we were talking about plasmas on Monday, and we showed on Monday that we could have a microscopic model, that was the Drude model, that allowed us to obtain a skin depth. Okay, and that skin depth arose because we had frequencies for the electromagnetic radiation which were not much greater than the collision frequency. The collision frequency was important. Okay, so today we're going to do. So I think it's one of the most interesting areas of plasma oscillations is the high frequency situation. So what do we mean by that? Well, remember our statement about frequency is related to the collision frequency. And what does that mean? It means that the electric field, remember this is considering a monochromatic wave as our sort of template, the electric field direction is changing sign quicker than a collision can occur. Okay? So this can occur in any plasma. What we're doing is we're setting the frequency for which the plasma may be considered collisionless. Okay? So we label this situation as being a collisionless plasma. Right? In other words, the electric field is causing each electron to move with respect to its stationary ion partner, but the electrons never move fast enough that they're going to hit anything. Okay? Now there are other kinds of collisionless plasmas, so I'm just going to note that this is one kind of that. Okay, okay, now we go back to our old friend the dispersion relation, and we can write down a statement which is that we can write down that the permittivity is now something like 1 minus omega p squared over omega squared. Okay? If you look back at previous notes, you can see this is the case. Right? So this is a statement about the permittivity that we can make. Now notice a very, very important statement about the permittivity in a collisionless plasma. It is real valued. So therefore, there is no absorption of energy. So this is what distinguishes it from the collisional case. So in the collisional case, there is an absorption of energy because there are collisions occurring. Here there is not. That does not mean that we must always have transmission. So we can write that down equivalently in terms of the refractive index, and we remember that the refractive index can be expressed in relation to the speed of light. Okay? And we can therefore relate the wave number to the permittivity, which is on the right hand side. Okay? It's 1 minus omega p squared over omega squared. Okay? So this is our statement about the dispersion relation in a plasma. So we write down omega squared equals k squared c squared plus omega p squared. Okay? What is this saying? So this is the dispersion relation. This is a very important thing for you to remember in a plasma. So omega p is the natural oscillation frequency of electrons in the plasma, and that's determined by the density of the electrons in the plasma. Omega is the frequency of electromagnetic radiation that we're trying to send through the plasma. And K is the wave number that tells us the resulting wavelength of the waves in the plasma. Right? So really we should write it down in another form. So it's often written that way around. We should really write it being down as this form. Plus or minus 1 over c. So obviously the waves can be going left or right through the plasma. Okay, forwards or backwards. Omega squared are driving frequency, omega p squared, which is the natural frequency that the electrons want to move at. Of course, there's a square root there. Okay. So straight away we can see that we should be seeing different regimes. We always consider low and high frequency regimes, as we always do. So we're going to look at it in a slightly different way this time. We'll think about, firstly, the large K situation. Okay, remember that K is 2 pi over lambda. So a large K is a small wavelength. Okay. What does that mean? A large K is a large frequency, a small wavelength. And that means the frequency is large in comparison to the plasma frequency, and that means the electrons aren't really doing very much, and that's our free space condition. Okay? So omega squared is much bigger than omega p squared, so the electrons don't really do anything, they don't move around very much. So the response of the plasma to the incident radiation is like it was a vacuum. Okay, that makes kind of sense, doesn't it? Electrons don't do much. The other situation is when K tends to 0, which is clearly a large lambda, a long wavelength. And in that situation, omega squared becomes comparable to omega p squared. I'm just looking at that expression for the dispersion relation. And that's what's happening there, is that remember, this is all, the electrons are still not colliding with each other, but this is a lower frequency. The electric field is varying slowly enough that the entire plasma, all the electrons over large distances, will move along with the electric field. Okay? So a large wavelength over a large distance, the electric field will move all the electrons together, and they all move at the same frequency as the plasma frequency. But in all these situations, we just remind ourselves, epsilon r is always real. Okay? As long as omega is much bigger than the collision frequency. Okay? Now, we notice that there is a slight conundrum here. We notice everything is fine, right? For omega is bigger than the plasma frequency. Right? N is real. But there's another situation where omega is less than the plasma frequency. What happens when I have an electromagnetic wave incident upon a plasma, or trying to be generated in a plasma, whose frequency is less than the plasma frequency? Well, in that situation, N, the refractive index, becomes imaginary. Okay? So the top case is easy to fathom, isn't it? That's real. The wave can propagate through the plasma and there's no absorption. If it's imaginary, well, there's no process of absorption. Okay? In both cases, there's no absorption. So what's happening in the imaginary case? Sorry, I've run out of space on the paper there, haven't I? Well, there must be reflection. Let's try and draw that out. Carefully. Let's try and draw omega versus K. Okay? So when you look at these things, this is dispersion relation. These dispersion relations here, they're simpler ends of more complicated things you can draw. Okay, we'll see a dispersion relation in a waveguide later on. Let's plot omega versus K, and to begin with, what we'll do is we'll do a forward-going wave and a backward-going wave. Okay? And those dotted lines are meant to be the situation of free space. Okay? So in that dotted line is omega equals Kc, and obviously minus Kc on the other side. Right? So those are our two directions. So clearly the gradient of that line is C, obviously. Yeah. So that's what would happen if there was no electrons being able to be moved around. But as we saw from our dispersion relation, for very long wavelengths, so long wavelengths in the middle, and short wavelengths are out to the edges. Okay. for a sufficiently long wavelength, all the electrons will move at the same frequency as the driving frequency. Okay, so we plot it this way round, but really it's the y-axis, the ohmic thing that's doing the driving, and it's the k that's the response. So you can see as we change the frequency, if we have a high frequency, it's like vacuum, we're up here somewhere. Okay, so we should have an asymptote. Goes up like that. And as we drop the frequency, eventually the plasma oscillates all together along with the incident wave. And of course, it will do the same thing for it's going the other way. Okay. And we have transmission up here and reflection down here. So there's no propagation for a driving frequency below the plasma frequency. Now, there's a couple of extra things we can put on. We can say, let's choose a particular frequency. Say that one there. Okay, so I'm given omega. And we can do two interesting lines. We can do this one here. So the gradient of that line is the phase velocity, omega over k, which is bigger than c, isn't it? And the tangent to the line, that's obviously d omega by dk. That must be the group velocity. Okay. Right. And we notice that in a plasma, the phase velocity is always bigger than the speed of light. Unfortunately, the group velocity is always less than the speed of light, which is the important bit. Okay. And clearly, as we approach omega p from above, the phase velocity goes up to infinity. Okay. What does that mean? That means that as the frequency falls to the plasma frequency, the plasma starts to respond all together. So any change at one end of the plasma is immediately also the same change at the other end of the plasma. That's what we mean by the phase velocity. But the group velocity, our ability to transmit a signal from one end of the plasma to the other, must fall to 0 at the plasma frequency. Okay. Slightly counterintuitive. All right. Okay, that's one way to draw that curve. Now, there's another way to draw it. We can also draw it this way. Perhaps a little more intuitive. Here is our driving frequency, omega. And here are those velocities. So we see that there is a boundary there, right? Below a certain frequency, below the plasma frequency, there is no propagating wave. And at very high frequencies, the group velocity and the phase velocity must both be equal to c, so there must be some asymptote there. Right? Okay, so we say that as omega tends to infinity, Vp equals Vg equals c, as it should do. Okay. That's a dispersionless system. Right? There's no dispersion of the different frequencies with respect to each other. They don't propagate differently. But as we go to lower frequencies, the different frequencies will have different velocities, so they disperse from each other, hence that dispersion relation term. And that's our group velocity, and that's our phase velocity going off to infinity at omega p. Okay. So I haven't yet explained, have we, what that situation below omega p looks like. So one more time, just to keep you in tenterhooks. Okay. Omega greater than omega p. Okay. The waves are propagating without attenuation, but this is dispersive, by which we mean that the phase velocity varies with frequency, okay, which it doesn't do in free space, but it does in the plasma. And k is real, okay, and therefore there's no damping. Okay. It might be damping for other processes, but in this simple model, there is no damping because there are no collisions, and at large frequency, the electrons are not moving much, so it becomes like a vacuum. Right? At omega less than omega p, that's one that's a bit weird. Well, of course, this is an evanescent situation. Okay. So I'll go to a fresh piece of paper there. Okay, it's an evanescent situation. In this case, K is purely imaginary. K is purely imaginary. So we can write it as we normally do. K equals minus I alpha, where alpha is some sort of real number. So that E varies something like e to the minus alpha z through the plasma. Okay? And as you would imagine, there's no propagation of the electromagnetic wave, and there is no energy transfer because there is no process for the energy transfer to occur. A concept that we'll refer back to later. And therefore, any wave incident on a plasma that has a frequency omega, which is less than the plasma frequency, must be being totally reflected. Okay, that's a physical consequence. The physics consequence has to be like that. Okay. So let's look at a few examples. So, let's get a sheet of paper. Ooh, where did that come from? So we'll look at a metal. Copper is a good example. Okay. So in copper, the collision frequency is something like 10 to the 14 per second. And we're going to consider light which is several eV. Okay, so of the order of 10 to 16 hertz. That's roughly in the visible range. And the plasma frequency is about 10 to 16 hertz. Okay, so if we compare that to UV photons, which have similar frequencies, we can see that they will be transmitted. So copper is transparent to UV radiation. Okay. We simply compare the plasma frequency. So the plasma frequency comes from the electron density. Right? UV photons have a frequency which is bigger than that, so they will travel through copper. Seems a little counterintuitive. Okay. If I have frequencies which are below that, then those are reflected. Okay. So visible light should be completely reflected from the metal. Okay. This is why metals are shiny. Now at much lower frequencies, say gigahertz, okay, rather than tens of terahertz, we're now in that regime where the electrons are moving enough that the electrons in that metal start to collide. Okay, so this is frequencies like radio waves, and then we have a combination of that skin effect and reflection together. Okay. So we have two separate situations. We have a skin effect, which is an absorptive effect, and we have a plasma propagation effect, which is non-absorptive. Okay, now, this is a situation, let's bring that down. Let's look at the numbers. So we can see that the electron density is high enough to create a fairly high plasma frequency. Okay, so in the examples, which are in the notes, try to calculate the electron density. These are for the conduction electrons. Calculate the plasma frequency for those, and you'll be able to get these numbers out. Okay, show that you can get roughly these numbers out. So let's think about another example, which is a more tenuous plasma. Well, I'm going to talk about the ionosphere. So I'm going to sketch over this. It's all in the notes, but I'm going to talk you through this one. Okay. Now, what's happening in the upper atmosphere? So up there, above, say, 50 kilometers or so, there's quite a lot of UV radiation. Okay. Now, we already know that the states of matter that we normally see, solid, liquid, and gas, are transformed through the addition of heat. We already know that. Okay? So we have these four states of matter, okay, where we have progressively degrees of order in that matter being broken down. So in the solid to liquid, we're breaking down positional order, then we're breaking down distance order when you go to a gas, and then eventually the electrons have enough energy that they can be ionized away from the ions that they were previously attached to, and we have another state above that. Okay? Now clearly, the kinetic energy and the temperature are related to each other. Okay? So if we were to write down a relationship between the kinetic energy required to ionize the plasma, okay, the typical kinetic energy of the electrons or any of the materials in the plasma must be comparable to the ionization potential. We can convert that number, which is several eV, into an equivalent temperature, which must be tens of thousands of Kelvin. Okay? And I do point out that this separation between solid and liquid is not complete. And there's many PhDs you can do. Look at the liquid crystals down there. Okay, but we're looking a bit off the top. Okay. Okay, so a relatively high temperature of 10,000 Kelvin is nevertheless a relatively low average particle energy. Okay, now, in a fully ionized system, we have a thermal equilibrium, okay, where we have a typical kinetic energy, which is related to the temperature, but there's a distribution around it, which is Maxwellian, which you've seen before. Okay? And again, we said that we can relate the typical energy, which we believe here to be something like of the order of an eV, that corresponds to about 10 to the 4 Kelvin. So you can say that we can have a 1 eV temperature, which is equivalent to, if we were to touch this object onto something solid, equivalent to a temperature around 10 to the 4 Kelvin. Okay? So we tend to use that terminology on the left. Right? Now, the interesting question is, if you look at the upper atmosphere, right, what is the source of that heat? Well, the answer, of course, is the sun. Right? And there's an equilibrium formed between the photons which come from the sun and the upper atmosphere, because they're not really in thermal contact with what's underneath them. Okay? Right? So if you have photons arriving from the sun, they can cause ionization. And if you have enough of these 1 eV photons, or 1 eV-ish photons, to cause ionization, you have a Maxwellian distribution where you have a few of those electrons which have energies which are higher. Okay? All right, now, so this is our situation. We have the sun shining down, okay? You have an upper atmosphere which becomes ionized because of these photons falling upon it, and lower down it is not ionized. So you imagine that there are two things going on. You may have a varying amount of density of the atoms in the upper atmosphere, and you may also have a varying amount of ionization. Well, it should also depend, of course, on whether the sun is shining or not. So you expect there to be a day to night variation. Right? So this is what you see. If you actually work out what it looks like, it looks something like that. So there is the sun shining down. We get a degree of ionization, and the thing to watch out for, and I call your attention carefully to this, is you'll see these number densities given both in per centimeter cubed and per meter cubed. So obviously it's a 10 to 6 difference between those. And this is a rough sketch. There's a better sketch in the notes. Okay? And this vertical axis is in kilometers. Okay? So you can see that lower down, the density of the air is quite high. But what we're plotting here, this is the density of the electrons. And we conventionally describe those in 3 layers, where there is a maximum density, it's something like 200 kilometers above the Earth. So, what's the consequence of that? This is just what we saw before. The difference here is that the densities are much lower. Okay? The densities here are of the order of 10 to the 12 per meter cubed or less. So therefore, the kind of frequencies we're talking about have to match the plasma frequencies for those, and those are in the megahertz range, not in the terahertz range. They're a million times lower. A million times lower. Okay? So, because each layer has a different plasma frequency, then different frequencies will be reflected from different layers. So I should label 2 of them here. Okay? So the low density ones will reflect low frequency radiation, say megahertz, and the higher density regions higher up, okay, will reflect higher frequency radiation. So because these ones down here have already been reflected, this low density stuff up here doesn't really matter in terms of reflection. Sufficiently high frequencies, of course, will make it all the way out. Okay? Now the interesting thing here, these are the sort of frequencies which are involved in lots of radio communications. So this tells you that there's some boundary of radio frequencies you can get through the ionosphere, as it's called. So this is the ionosphere. Okay, now, let's put some numbers on that. So we had our plasma frequency given in 2 pi units. Remember, we can convert the plasma frequency by using a shorthand. And again, you will see this in the books. Okay, so if n is given in per centimeter cubed, then the plasma frequency is something like 9 kilohertz times square root of n. So if n was 1, the plasma frequency would be 9 kilohertz. It's quite a nice way to do it, right? You do have to watch out between this conversion between centimeter cubed and meter cubed and this square root. Okay, if you give it, so I've just put both there. If you give n in per meter cubed, then it's times 9. If it's in per centimeter cubed, it times it by 9,000. Okay, you might see this slightly more accurately written, but it's about that much. Okay? So you can see in our okay, so try doing this calculation. Take these frequencies, very quick calculation, right? Calculate the plasma frequencies for these different layers, and you'll see that the plasma frequencies are about 300 kilohertz, 3 megahertz, and about 10 megahertz. Okay. All right. And this tells you why you get reflection of these different frequencies at these different heights. Okay. But remember, there's a diurnal effect. This does vary as a function of time of day. Okay. I've sketched over that. Have a read through that, and see if you can follow through that calculation. It's definitely worth doing. Now, for future reference, we should also have a brief overview, if you don't already know them, of these so-called radio bands. Right? So we saw what the frequencies actually were, and I did mention that these correspond to radio bands. If you've ever wondered what you're listening to when you're listening to, if probably still listen to Radio 1, is it all internet-based? I don't know. In the olden days, of course, it was only radio. Okay, long wave. Very few people use that these days, but long wave is wavelengths which are quite long, as you would imagine, okay? And those are frequencies which are low, below about 300 kilohertz. Medium wave is still a longish wave of hundreds of meters, so you can see from our conversation about how we generate those, this must be the kind of scale length the device is creating those waves. Okay, so whatever's generating these frequencies or these wavelengths, it must have a similar scale length to the wavelength they're generating. So of course, as you go upwards in frequency, the wavelength is dropping, and TV sits around this region. Okay, right. So FM radio and TV sit around here. So your TV aerials and your radio aerials are of the order of 1 meter or less in size. Now, there's also propagation and absorption that we won't go into. Absorption becomes more important as you go to higher and higher frequencies. So the transmission over long distances goes down as you go up in distance, as you go up in frequency. Okay? Now, I put these up because we're going to talk about this when we talk about waveguides in the next section, in the 2 sections on, right? When we talk about waveguides, there are standard waveguide labels, and you should at least familiarize yourself. I'm not going to ask you to remember these, okay? But at least familiarize yourself that there are standard labeling, and they more or less go up in factor 2 in frequency, okay? An L band is the stuff that we use for mobile phones. Mobile phones run at gigahertz or so. Okay? And from this description, you can see that the aerials inside your mobile phone, in the back of there, which is somewhere here-ish, right? You can see that they have to fit inside your phone, so they must be of the order of centimeters in size. S-band, you probably haven't seen S-band very much, but S-band is basically what's inside your microwave oven. Okay? And C-band and X-band, they're used in radar. Okay, so communications, GPS, microwave ovens are here. So this is why this is called microwave communications. And these high-frequency things, they have shorter wavelengths which can be used for working out where stuff is and doing high resolution radar, so you can look at the shapes as well as the fact that you're having a bounce off an aircraft and things like that. And you can also use it for other applications as well. So that's the division. We describe it in terms of wavelength at the longer end, because that's a convenient number, and we describe it in terms of frequency in gigahertz at the upper end, because again, that's convenient. Okay? All right. So what's our summary of that section? So you can see that GPS satellites, okay, they transmit a signal that we receive down. Oh yeah, there it is. Yeah, GPS satellites they transmit a signal that we want to receive on Earth, so they have timed signals that allow us to triangulate and figure out from a collection of these where we are on the ground. Okay? We need to be able to receive those signals from the satellite in the sky, so equally, stuff being reflected back down to Earth, stuff coming from above the atmosphere, might also be reflected. That clearly has to be transmitted at a frequency which is above these reflection frequencies. Okay? So your medium and long wave signals do not get through the ionosphere. The short wave is bounced off the upper atmosphere, and the VHF gets through. Okay, so that means that if you're listening to your Radio 4 cricket on long wave, the aliens can't hear that, but they can hear Radio 1 on FM. Okay, all right. Okay. I'll try not to be funny too much because I'm not very good at it. But I'll try occasionally. Okay, now how do we actually measure these things? Well, what you do is you have a variable frequency transmitter that can vary quite quickly, and you can see that there are a variety of ways you can change the output frequency in the direction. Remember, we have those phased array things. We can send variable frequencies around the expected values of the plasma frequency. And what we do is we send a pulse at a given time, at a given frequency, and you see the time when it comes back, and you know the propagation velocity is basically c. And then what you can do is you can then work out the number density as a function of height. Okay? So that's called an ionosonde. A sonde, that's a French word which means probe in French. So just like when you do an ultrasound or an ultrasonde, you can do that underwater as well. Okay, so those sondes are usually underwater things, but here it's called an ionosonde because of course we're measuring the ionosphere with it. Okay, so I breezed over that. Have a read through the notes to kind of fill in that, but that's the basic idea of those two examples. Yeah, we did right halfway through. Okay. One more example. So we started with metals. And I will remark, where was our metals one back before, wasn't it? We remarked about metals that, I'll put it somewhere. Anyway, we talked about metals, and they had a very high very high electron density, and therefore a relatively high plasma frequency. A good question to ask yourself is it interesting that copper is a red metal compared to other metals, which are silver? Is that related to the plasma frequency? Kind of should be, shouldn't it? Could be that different wavelengths in the visible range may be around about that boundary in copper, and it'd be different in something like gold and different in other silver metals. Okay? Have a look around. How many metals are red and how many metals are yellow? Because most metals are silver in colour. So is that telling us what the electron density is inside copper compared to the other metals? Maybe it is. Okay? Okay, now, right at the other end of the scale is interstellar space. So we've seen high densities in metals, lower densities in the ionosphere, but still millions of electrons per cubic meter. Okay? Interstellar space has a very low electron density, but it's still over extremely long distances and long wavelengths able to have an effect. Okay? So one effect that it has is, imagine you have a pulsar, a neutron star with a small diameter, okay? And as it collapses, it starts to spin very rapidly, and we believe that the typical rotation rates are hertz to kilohertz. Okay? And one thing we see about these things is that the magnetic axis, which helps to beam the radiation, is not the same thing as the rotation axis. So therefore, we get pulses of radiation which are pulsed at the same frequencies as the revolution frequency of the surface of the star. Okay? Now, those pulses come out at discrete times, okay, because of the magnetic field. However, there will be dispersion because there are different frequencies being emitted over enormous distances. Right? So if we have, let's say we have 100 megahertz observation, so we have radio observation of the pulsar, that's much bigger than the plasma frequency. So we have transmission, but we can write down an approximate form for the refractive index, like so. So I want you to show that you can do that. Okay. And then if we pick two frequencies, omega 1 and omega t, from all the frequencies which are being emitted by that pulsar around this 100 megahertz regime, we'll see they should travel at two velocities related to the true refractive indices. Okay, so the frequency is omega. For each frequency, we got a different refractive index n. Okay? So over an enormous distance, we should get a difference in time caused by the difference in the refractive index multiplied by this enormous distance to the pulsar. Okay? Okay, clearly, we can relate some different things together. If we know the distance, and we know the plasma frequency, we can work out what the time difference is. Okay? But really, what we really do is we have some measure of the distance, we directly measure the time difference, okay? And if we know the two frequencies we're observing at, we can measure the plasma frequency. Of course, we can measure the plasma frequency, we now know what the electron density is. Okay? So we can measure the density of ionization in interstellar space, which is pretty cool. Okay? And you can measure it to be about 0.03 per centimetre cubed. All right? So for every 30 cubic centimetres of interstellar space, there's something like 1 electron floating around. Okay? So this is right at the other end of the range. Okay? So there's no reflection going. That's an enormously long wavelength. Okay? So you don't get any reflection of that. But you do get a variation of the refractive index. Now the number of atoms in interstellar space is something like 1. So that tells you that a few percent of those atoms are being ionized and have free electrons floating around. Okay? Where do they come from? They mostly come from dust grains. Okay, so this is quite an interesting topic in itself, but it's just another end. Okay, so we've been through a few, bits and bobs about plasmas. I thought those 3 examples would kind of help to illustrate it in a useful way. Okay, so we'll come back to this. What you should do is I want you to look to try to plot it. I think there was one extra plot I wanted to show you, which is in the updated notes. Yeah. In the updated notes, there is a plot, which I'd like to do, which is to plot wavelength and omega p, and you should see a boundary that looks like that. Okay? See if you can do that plot, and look in the notes, and see if you can replicate it. Above the line is either reflection or transmission, and below the line is either reflection and transmission. That will help you figure out which way around things are, because when you convert from wavelength to frequency, and you compare it to the plasma frequency, it can be a bit confusing at first. If you try to do that, it might help your understanding of it. But look in the back of the notes, and in section 3, and it will tell you that. Okay, so that's it for section 3. Now, those are plasmas. We should now look at reflection, refraction, and scattering. Now, reflection and refraction, we're going to look at that in more detail when we look at waveguides. So we should think of this bit as being more to do as a preliminary. The scattering we talked about earlier on when we talked about the generation of radiation and how we expect that if an electromagnetic wave is incident upon a medium, then the movement of the electrons will cause radiation, and that is the same thing as scattering. Okay, so we're going to cover both those ideas. Okay, so shall we dive in? So let's talk about reflection, refraction, and scattering. So the first 2 bits, of course, you've covered before. Okay, so this is partly revision, but we're thinking about EM waves going across an interface, of course. So in section 3 we talked about the behaviour of materials which had a single permittivity and permeability, okay, across interfaces. But now we're going to look at boundaries. So as normal, we consider an incident plane wave. But now we have an extra physical parameter, which is the orientation of the plane wave with respect to the boundary, in other words, the angle. But as we normally do, we're going to consider homogeneous, okay, isotropic, and linear media, because otherwise there's a whole host of other things which are beyond the scope of this course. And we're also going to consider a plane interface, remembering that non-plane interfaces can really be considered as a series of small planes attached together in some way. Okay, that's optics. We're not going to do that. Okay, we're considering the strength rather than the focusing. So we've seen this stuff before. We need to consider the boundary conditions at that surface. Okay. So in this course, we're going to consider at medium 1 and medium 2. That's our labelling. Medium 1 and 2 below. And the interesting, if we consider the plane wave coming in, it could be oriented at some angle. Okay? And if it's a plane wave, we can consider its components either parallel to or perpendicular to the surface. Okay? So one is what's going on in the medium 1 on one side of the boundary, and of course there are corresponding magnetic fields to go with the electric fields, and we've got the same thing on the other side. Okay? So that's our labelling scheme. Now obviously we can relate the components of E and B across that interface, because we can apply our boundary conditions. So this is revision. So this is it's in several versions of the notes. Okay. So I'm going to put them up, knowing that you have seen these before, so we can just describe them as we go. Okay. So when we apply boundary conditions, what we're doing is we're applying Maxwell's equations, seeing what they tell us in their integral form about what's happening across a boundary. Okay. So the first thing we can apply is we can apply Faraday's law. So here is our quasi-planar interface between the two media 1 and 2. And in this case, we're thinking about a loop that goes around some segment of plane with area A, and we're counting up the electric field on one side, E1, with the electric field on the other side, E2, over some distance L. Okay. So remember that Faraday's law allows us to relate the electric and magnetic fields together. So we have the integral form of that, which relates the electric field around the line to the integral of the magnetic field across the surface, at least it's time variation. And one thing we say straight away is if we allow this area to go to 0, this right-hand end goes to 0, and if we allow this line and this line to approach the surface, these two components here also drop to 0. So whatever E1 times L across that little short length of line, that length of line are doing on one side, this one must add up to be the same as that one, it must add up to 0. Okay? So therefore E1 is equal to E2. So the parallel component, remember this E1 along the surface, that's a parallel component, must be continuous across the boundary. We've seen that before. Okay. Okay. Next one. Okay. Gauss's law. Surface between medium 1 and medium 2. Now we have a volume. We're going to say it's a thin pillbox. What I mean by that is it has two surfaces of arbitrary shape, okay, with an area A, encompassing a volume V, which has some height between the two surfaces L. Okay, so we've got A across the surface and L between them. And now we consider the normals to the surface. So we've got on the side, on medium 1, it sticks out perpendicularly, that's ds. The other side of normal to the surface sticks out the other side. And what we're interested in is how to relate the electric field pointing through the surface on one side and the electric field pointing into the surface on the other side. Okay? And we can write Gauss's law for a particular medium as being equal to the divergence of the permittivity times the electric field is proportional to the charge. So we can rewrite this in this integral form and add up the electric field pointing out of the surfaces to be dependent upon the charge in the volume. Right? Okay, now we do the same trick we did before. We let L go to 0, and then we can add up the perpendicular component because of this dot product. Okay. We have a certain amount coming out of surface 1, that's on the left hand side, and a certain amount going in surface 2, that's why there's a minus sign. That must be equal to the surface charge density, because as we let these two surfaces approach each other, as L goes to 0, we have a surface charge density, and we let the area go to 0, that cancels out. Okay? So therefore, we can relate the electric field coming out of one surface to the electric field coming in at the other surface, and their difference must be the charge density. Okay? When scaled appropriately by this epsilon value, that's the displacement vector value. Okay? Right. And of course, the special case there is that when there is no surface charge density, and the perpendicular component of the electric field is continuous. Okay. So we've seen that before, yeah. All right. Okay. Next. This is a quick one, because all we do is we say, if it's a magnetic field, we can do exactly the same thing, and B perpendicular is continuous. Okay? So exactly the same argument. Right. Next one. This is a bit harder. This is the more interesting one. So we do the same trick again. And now we're looking at the magnetic field, or at least the driving term H, going across this boundary between the two media, and it's a loop again. We draw a loop, and it has some distance h that we traverse from one side to the other, which of course is going to go to 0, and we have a distance along L. And we can think of the reason there being a difference between H1 and H2 is that there could be little currents flowing along the surface. So we can relate curl of H to the currents and the rate of change of whatever electric field is going on. That's one way of writing that. Okay, you can also write it down in the traditional way. Okay, so those two statements, this equation, are the same thing, aren't they? Okay, and that's a relative permeability there. All right. So we do the same thing. We integrate over that surface. Okay, that's a surface here with area A. Okay, proportional to H and proportional to L. We do that, and the first thing we do is when we integrate the curl of H over that surface A, we can turn it into the line integral around the boundary of that surface. Okay. So remember, this dl is all the way around. Okay, that's Stokes' theorem. And we can relate that to the amount of current flowing through the surface and this time variation of the displacement vector, which we know that as L goes to 0, that will disappear. Okay? So you can see that that's what these little dots are representing up here. They're representing the amount of current that's flowing through that boundary along the tangent of that boundary. Okay? So we've got the magnetic field coming in from each side, and this is the current at right angles to it. Okay? That's the geometry you need to bear in mind. Okay? So we let H tend to 0, so we count up the total amount of current along that surface, and that's this integral on the right here, and that's going to be related to the amount of H going around that boundary. Okay? So we have the same thing we had before. We can say that if we have a certain amount of H on one side, that's along this boundary here, okay, times L, take away what's happening on the other side, it must be equal to the amount of current flowing across through that surface along that boundary between medium 1 and medium 2. Okay? So therefore, the difference between the magnetic field on one side of the boundary compared to the other must be equal to the current flowing at right angles to it. That's what it means by those parallel and perpendicular components. So far what we've done is we've said, actually, we've said that H, okay, is in the same plane as this surface. Okay, so H comes in, crosses these boundaries, and we integrate it around that boundary, and we relate it to the current which is going perpendicular to it through that surface A. Okay, so that's clearly one of the components you can have. So in general, if you have an arbitrary vector form of that, then the difference in H in any particular plane must be related to the current flowing perpendicular to that plane. Okay, so we can say, if we can draw a normal to that some surface, we can relate the difference in H across the surface, okay, to that difference. This is saying that basically whatever the difference in H is equal to the current flowing at right angles to that difference. Okay, right. That's a preamble. Have a read through of the notes and just go through that one more time so that you're happy with that. Okay, hopefully that's all familiar. Now there is something that we need to remark on before we finish today. Okay, we notice that this is a surface current. Okay, so we're saying that if there is going to be a difference in the magnetic field from in medium 1 to medium 2, it's produced by there being a current on the surface between those two media. And that's an important thing to note. Because our whole concept of what a surface current is, it's a finite current that occurs in an infinitesimal layer of material, right? So if we have a surface current density, that can only really exist if we have a perfect conductor, okay? If the conductivity is infinite. Right? However, if we have a finite conductivity, then an infinitesimally thin layer cannot carry any current at all. Okay? So if we have a perfect conductor, we can maintain a difference in the magnetic field across the boundary. But if we have a finite conductivity, then the parallel components of H across the boundary must be equal to each other, which is a little counterintuitive to start with. Okay? All right. So that's our preamble to kind of get you in the mood. And then we're going to obviously the next stage is to take that revision bit and we're going to look at how much of each wave component we have going across. Okay, and we'll quickly dive into the statements about how that relates to transmission lines and waveguides, which we'll do later. Okay. But just have a look over that one for yourselves in the notes, just to re-familiarise yourself with it.
How does the atmosphere get more dense further out?
Oh no, the atmosphere doesn't get more dense. The ionization gets greater. So, at lower altitudes, the density is higher, but you have less ionization. So the air density is higher, but the electron density is lower. So there's
more free electrons further up.
That's right. So there must be a peak somewhere. So when you're very high up, there's a lot of ionization proportionately, but there's no air to be ionized. So it must drop off to zero at some point. Yeah. It's even more complicated than that. Okay. Because there's all sorts of other weird stuff that goes on there. What you have to remember is, as well as photons falling on the Earth, there's also charged particles.
Thank you.